We'll take a break here in a little bit. So on 3.3, what you're doing is this section right here is a super important section because it's the fundamentals of working with derivatives and just basic derivative rules. The first thing I want to kind of mention is the different type of notation. So far about all we've seen is f prime of x. You can also say y prime, or you can do this. I don't think we've seen this yet. We call this Lightness notation. That's the notation that Gottfried Leibniz came up with. And calculus has sort of two co-inventors, Isaac Newton and Gottfried Leibniz, actually at the same time in history. Both independently worked with certain ideas in calculus. And Leibniz used this notation. I use both. You want to know how to use both because it's important. So all this Leibniz notation just says is the D stands for derivative, so it's derivative of the function y with respect to the variable x. Okay? You'll kind of catch on to that as we go and what we use that for. Okay, so here's your two basic rules that we're going to look at. And this one, the first one is the constant function rule. And this just says if you have a constant, if that's your function, then the derivative of that is going to be 0. It always will, okay? And here's the reason for that. Okay, say for instance you had f of x is equal to 3. That's a constant function, right? Which just means it's a horizontal line. So if you looked at a graph of a horizontal line, and I wanted you to find the slope of the tangent line, what would it be? 0. And everywhere it would be 0. The tangent line on that's always the same. The tangent line to a line is the same line, so you would say f prime of x is equal to 0. It always is. So anytime you have a constant, derivative is 0. You know that immediately, see, okay? You don't have to do a difference quotient on that. Okay, the next thing, which is really nice, is the power rule, okay? The power rule says if your function looks like this, if it's f of x equals x to some power, and we kind of start off with that being a real number, just any real number, then what you do is this. When you do the derivative, it's real simple. What you do is you knock off the exponent and put it in front, leave the x, and then you always subtract 1 from the exponent. That's the power rule. You'll do that over and over in calculus. It's a very simple rule that we're going to work on a little bit here to start with today. So those are the two rules we want to look at, and I'll give you a quick example of the power rule. Say you have x to the third. Okay, remember what we did when we in an earlier section. We put it in the difference quotient. Took us a while to get through that difference quotient, set the limit of h equal to 0, and get the answer. Now look what you do. It's easy. You just go, knock down the 3, subtract 1 from the exponent to get 2. Problem done. Isn't that great? Yeah, okay. All right, so that makes it easy. Okay, I'm going to prove the constant function rule. Okay, I'm going to do a couple of proofs. So what we want to do on this is let's just write down f of x equals c. Okay, c is going to represent a constant. I'm going to prove to you it's 0. It's obvious that it's 0, but let's prove it. If you're proving these things, you always go back to the difference quotient, the definition of a limit. So if we did f prime of x, it would go like this. We would do the limit as h goes to 0 of f of x plus h minus f of x over h. So that's how we need to start that, and then we just need to work it out. And it turns out that it's real easy. The proof on this is super easy, actually. Okay, so let's get the difference quotient set up. Okay, so let's see. Like I taught you on this is you just get those two things put in. Well, what would go there? What's the function? C. What do you think f of x plus h is? Still c, right? Can't be anything different. You can't replace the x with x plus h because there's not even x there. So look what you get. You get the limit as h goes to 0 of 0 over h. So of course that's equal to 0, right? Okay, because 0 over h is 0. You're just doing the limit of 0 as h approaches 0 like that. Okay, that's how you prove that that's always the case. All right, so you know that rule. I won't do the power rule proof because it's a little harder. So let's go down and let's now do some derivatives and kind of get this stuff out of the way. Okay, so I give you a function, you give me the derivative. That's what we're doing right now. Okay, f of x equals 10. What's the derivative? 0. It's a constant, right? You got a horizontal line, therefore the derivative is 0. G of x equals 3/4. What's the derivative? 0. Again, 3/4 is a constant. There's no variable in it. Okay. The next one, we have y. Now this time I'm going to do Lightness notation, just for something different. If I want to represent the derivative in Lightness notation, I say the derivative of y, that's the function, with respect to x. Okay? I'm just assuming it's x. What's the answer? 0. 2 pi is a constant, right? Pi is not a variable, it's a number. Okay, so we have that. All right? So those are easy. Okay, now let's go to g prime of x. Now this one is the power rule, so what's the answer?
5x.
5x to the fourth, good. Power rule's real simple. You knock off the exponent, and then in your mind, you don't have to write that step, you just in your mind make the exponent go down 1. There's your derivative. All right, piece of cake, isn't it? Power rule's awesome. Okay, now let's go through, we're going to do a little bit more with this. A couple of things I want to review, because sometimes students get in calculus and they'll forget a few things. One thing that you're going to do a lot in calculus when you're working with derivatives is working with negative exponents and radicals. So just a couple of algebra things I want to review here. All right, the key thing I want to show you is if you had, just as an example, like 1 over x to the second. You can rewrite that. Anytime you move that up, the exponent changes to negative. Okay, that's just basically the rule that you've learned in the past, is you can change a negative exponent to a positive. Okay, so for instance, if you had x to the negative 7, what's that? 1 over x to the positive 7. You need to know that. Okay, does everybody remember that? Okay. You must. Okay, all right. All right, so that's kind of what that one's saying. This one's just saying this, okay? If you started with a negative exponent down there, well, if you move it to the top, what does it become? X to the second. Okay, anytime you change the place it is in the fraction, it just changes from negative to positive. So it changes signs. That's what happens, okay? All right, the other thing we want to look at is you want to remember a square root is the same thing as something to the 1/2 power. So the basic idea on this, if you have the square root, and I don't care what you have, if you have the square root of x plus 1, for example, you could rewrite that as x plus 1 to the 1/2. A square root is a 1/2 power. It's understood that you don't write the 2 there, but technically what it is saying is you have the x plus 1 to the first power, and then the second root like that. All right, you guys done that and remember that in your past? Okay, square roots are the same as 1/2 powers. Okay, they mean exactly the same thing. So if you had square root of 2, that's 2 to the 1/2. It's the same thing. If you did those two things on a calculator, you get the same answer. Okay, and then this is the more general rule, which says this. For instance, say you had a 5th root of x to the 3rd. Okay, you need to learn how to change that into this rational exponent form. So what you say is x to the 3 over 5. The name of the root is always going to be the denominator, and that exponent is always going to be that. So you have to do that in calculus. You do that all the time. Now sometimes I see students need to refresh their memory on that a little bit. Does that look good to everybody? Okay. Now we're going to use these kind of ideas on these next derivatives. So we'll kind of go through and work on some more derivatives. Okay, first of all, this one's in Leibniz notation. And when you see d over dx, that means you need to take the derivative. That's just the language of your job is to take the derivative. If I say dy over dx, that's really you're telling me that's what the derivative of the function is. d dx is a operating symbol. It just says take the derivative, okay? How would you do the derivative of y to the negative 3? We only know 2 rules, constant rule and power rule, so that's a power rule, isn't it? Okay, so we apply the power rule. So again, you bring the negative 3 down, okay? and then you subtract 1 from the exponent. And as you learn this, be careful with subtracting 1 from the exponent. So that's negative 3 y to the negative 4. Okay? The exponent always goes down 1. So down 1 from negative 3 is negative 4. Now, you could write the answer that way. You also want to know that you could also do this. If you bring this y to the 4th down, what happens to its exponent? It becomes positive. So you want to know that as well. Okay? Either answer is okay. Okay? You can't usually I tell it depends on the situation as what you do with that. Okay, now the next one, the thing on this is you want to make sure that you don't do this first of all. A lot of times I'll see students go 1 over 10 x to the 9th. Seems logical, you know, but that's not what the power rule says, okay? What you have to do on this instead is, and this has got a mistake in it, see how that's an x and that's a t? That's bad, okay? Actually, if I wrote it that way, the answer would be 0, but you don't need to worry about that now. So let's change that to an x, okay? That needs to be ddx. The variable needs to match that operator. So here's what you would do. You want to change this to x to the negative 10. So you want to bring that to the top of the fraction, okay? Then you do the derivative. Now, what's the derivative? Yeah, good. Okay, so you just bring that down. The first step is negative 10, x to the negative 10 minus 1. You don't have to write that step. You can do it in your head. So it's negative 11. That's okay to stop there. Probably on this one, I do like you to go ahead and go down and write things as positive exponents. So that would be kind of the preferred way to write the answer. Either one's correct. It's just different forms. Okay? All right, does that look okay? All right. Okay, now let's work with radicals a little bit here. Okay, so if you're doing a square root of x, and you're going to use the power rule, what do you have to do first? You have to write it as x to the 1/2, right? You have to. So you have to know how to change a square root into its exponential form. Okay? Now this time I'll do y prime. Okay? I'm just doing different notations to get you used to that. So what we do is we bring down the 1/2. So that's 1/2 x. And then you're going to subtract 1. You'll learn to do this in your head. I'm going to show the thought process on this. So you would have 1/2. And then you have to get a common denominator there, which is 2. So what you really have is 1/2 x to the 1/2 minus 2/2. So that gives 1/2 x to the negative 1/2 like that. Now that would be one way to write the answer, basically, is like that. Okay, that's one acceptable way. Okay, does that make sense to everybody? Okay, you're just subtracting 1, so you have to use a common denominator. Now the other way, if you wanted to make that negative exponent positive, you'd want to also know to take it to this stage. You'd want to say 1 over 2 x to the 1/2. That's another way to write the answer. You could do that. Then you could go further and you could change that back to a square root, so you could write it as 1 over 2 times square root of x. You don't have to worry about rationalizing denominators. You don't generally do that. In this case, your derivative, you can write it in any of those three forms. Okay, you just need to know when to do that. Okay. All right, does that make sense on that? Okay. Okay, just get into fraction arithmetic. Okay, let's look at the next one here. So the first thing you would have to do, how would you write the cube root of x to the second? X to the 2/3, right? Okay, you want to make sure you do that the right way. Don't get those numbers backwards. Just remember that the root goes with the denominator like that. Then what? Bring it to the top. You got to make it x to a power. You can't use the power rule unless it says x to a power. So you have to say x to the negative 2/3 like that. Okay? Now I'm going to do the derivative. So this time I'll say, okay, f prime of x, that's the notation that I'm going to use. Bring that down. That's negative 2/3. X to the negative 2/3 minus 1. Now this is what I start telling students to do. Don't go through the step of getting the common denominator. That's just 3/3, right? If it was 1/4, then you're going to use 4/4 and so forth, right? Okay, you'll learn to do that in your head, which I don't care if you do, but that's the idea. That really right there is a 1. So you have negative 2/3 x to the negative 5/3, like that, and that would be one appropriate way to write the answer, okay? Then you could also bring that down, and you could write it as negative 2 over 3x to the 5/3, making the negative exponent positive. And then you could also take it to this direction and say negative 2 over 3 and then change it back. So the cube root goes there, x to the 5th, and you could write it like that. Okay? And you don't have to simplify that radical or anything. Anyway, those are three forms that you want to work with when you're working with radicals. Okay? So the power rule, you get into arithmetic issues with fractions and negative numbers, but it's always doing the same thing. All right, does everybody follow all the arithmetic I'm doing? Okay, calculus is not hard, it's just there's arithmetic issues. Okay, so let's do this one here. Then I'm going to let you do a few problems, then we'll take a break after you do some problems, okay? All right, what's the answer to this one?
2 pi.
I knew someone would say that. That's why I asked. That's okay. It's not 2 pi.
0.
It's 0, okay?
That's right, that's constant.
That's okay. All right, that's fine. I do that on purpose. I'm not trying to trick you. Okay, so no, 2 pi is not right because pi is not a variable. It's a constant, right? So if you're doing a derivative of a constant, you get 0. Okay, right? Okay, so if you had pi to the 10th, what's the derivative? 0. Don't fall for that. Okay, I like putting that on the test. Not trying to trick you. Just trying to make sure you're paying attention. Okay? Okay, I'm going to let you guys try just down to number 8. Don't worry about number 9 right now. Well, hold on. No, do 9. Yeah, I want you to do 9. So let's work on this for a little bit.
What's going on with number 5 and 6? There's that random f prime of x in the middle there.
What I'm wanting you to do, that's a good question. Real good question. So, yeah, that's kind of a random thing that kind of got out of whack there. Sorry about that. Okay. I just want to make sure you have the arithmetic down. So what's answer number 1? What's answer number 2? Oh, fantastic. Nobody did 5e to the 4th, right? Okay, I bet somebody did somewhere. Okay, e is a constant. Okay, e is not a variable. Okay, next one, what's its answer? 12x to the 11th. Okay, then the next one, you go 1/4, x to the 1/4 minus 4/4. I just go ahead and do it like that. Okay, you're subtracting 1, so use 4/4. Okay, so that's going to give 1/4 x to the negative 3/4 like that. Okay, and that's fine. I mean, what I want you to know how to do with that one is that's kind of the general power rule. And then from there, if you didn't do that, you want to go ahead and write this as 1/4x to the 3⁴. Now, you don't have to change that to a radical. If you did, that's okay. What we generally do is if it's in an exponential form to begin with, generally I tell students to leave it in an exponential form. If it starts in a radical form, get the answer in a radical form. That's generally the approach I want you to take. All right? Okay? All right, the next one. How did you start number 5?
X to the negative 5.
Yeah, you got to bring that to the top. So you're really doing y equals x to the negative 5. Okay? Now, when you do your derivative, you're going to have negative 5 x to the negative 5 minus 1, which you can do in your head. So that's just negative 5 x to the negative 6. That's okay. That's one way to write the answer. What's another way? Negative 5 over x to the 6 like that. Okay? Those are the two ways. Okay? Is that solid? Okay? There's a mistake on number 6. Does anybody see the mistake? Not t. I don't know why I did that. That's 2x. And then you had to start by writing that as x to the 1/3. You have to do that. Okay, now your derivative is going to be, I'm going to just write this as 1/3, x to the 1/3 minus 1, so I use a 3/3. So that'll be 1/3 x to the negative 1/3 like that. So that would be one appropriate way to write the answer.
2/3.
Oh, 2/3, okay, yeah. Gee, I'm recording too, that's embarrassing. Okay, so we got negative 2/3. What's the other way? Well, we can just go 1/3 x to the positive 2/3, like that. And then this started in radical form, so my preference is you just go ahead and do 1 over 3, then you do cube root of x to the second like that. You want to take that all the way like that. All right? Does that look okay on the radicals? Sometimes students, when they're learning this, don't do the radicals right because of the fractions. That's the only issue. Okay? Okay. What's that?
Negative 2/3, where you just like.
Oh, right there. I erased it. There we go. Now we're good. Okay, and number 7, let's see. First of all, you want to write this one as, and ddz, see the variables match. You want to write that as z to the 5/6. Okay, then when you do the derivative, you're going to bring that down and you would have 5/6 z to the 5/6 minus 6/6. So that's 5/6 z to the negative 1/6 right there. So that would be one way to write the answer. Okay, you could also write this as 5 over 6 z to the 1/6, making the exponent positive. And then from here you could write this as 5 over 6, and then that would be 6th root of z like that. Okay, so those are the different ways. Are the radicals going okay? That's usually a little bit of a problem area when you begin doing this, but it becomes second nature. Okay, this one you would write as 1 over x to the 1/2. Then you would need to write it as x to the negative 1/2, right? Now you're ready to do your derivative. So when you do your derivative y prime, bring that down. That'll be negative 1/2 x to the negative 1/2 minus 1. So I'm using 2 halves. So that's going to be negative 1/2 x to the negative 3 halves. So that would be one answer to the derivative. Other way would be negative 1 over 2 x to the 3 halves, like that. And then you can change it back to a radical, so that would be negative 1 over 2 square root x to the third like that. Okay? Is that okay there, buddy? It's a lot of times algebra issues that some students have with radicals, so I just wanted to give you time to do that. Okay, f of x is equal to negative 2, what's the derivative? 0, of course, okay? The graph of this, if you graphed f of x equals negative 2, it goes like this. So what I'm just trying to have you do on this is f prime of x is equal, hold on, what am I trying to do here? Okay, I'm trying to graph the function. I'm not at the derivative. So that's the graph of f of x equals negative 2. So what's the slope of the tangent line at any point on that graph? 0. Okay, that's the key. You just want to remember that in case you forget that the derivative of a constant is 0. Just remember what you're doing as you're finding the slope of a tangent line to a horizontal line. So that's the idea. Okay, so are we doing okay with that? Okay, that's incredibly important because we kind of talked about graphs of derivatives. Now we're going to be precise on this next here. So the first thing I want to do with this example is just go ahead and graph that function. Now that's a quadratic. So you can make a table of values on this quadratic if you want to. I'm just going to do that real quick just for some accuracy. So let's use like those values right there and just plot the quadratic real quick. So you just do this in your head. If you square, 2 squared is 4, 1 squared is 1, 0 squared is 0, negative 1 squared is 1, and so forth like that. Now this is just the basic squaring function. Let's go ahead and graph the parabola. Let's graph the function that we have there. So that's negative 2, 4, negative 1, 1, 0, 0, and so forth. Just kind of plot the points. Now, I probably have said this before. Sometimes students have never caught on to this, but I want to say on a graph of a parabola, it just goes like this. If you go over 1, you go up 1 squared. If you go over 2, you go up the square of 2. So if you go over 3, how high up would I go? 9. If I go over 4, how high up would I go? 16. Okay, that's a squaring function. That's the way that works. So it's kind of nice to know that so that you can do that graph like real quickly. So that's the parabola. All right, now what we're going to do is, well, we can find the derivative now. So if f of x is x squared, then what's the derivative?
2x.
2x to the first, right? So that derivative, just power rule, you're bringing that down, so that's 2x. Well, that really would give you 2x plus 0 if you want to think of the y-intercept. So let's go ahead and graph that now. So let's graph this function, and that'll be the graph of the derivative. So you have a y-intercept of 0. You have a slope that's rise over run, 2 over 1. So from that point, you're just going to go up 2 over 1, up 2 over 1, and so forth like that. Okay? And then we're just going to plot that, and then that will be a very, very precise graph of that derivative when we do that then like that. So that'll be the graph of that derivative. Okay? It's very precise. Okay? All right? So what I have on this is the function, f of x, and then this is the graph of f prime of x like that. And that's one of the things I was trying to show you that will help you when you graph derivatives. If it's an x squared, the derivative goes down to a first power. If it was a fifth power, the derivative would go to the fourth power, just because of the way the power rule works. Okay, does that make sense to everybody? Okay, so that's the graph of the derivative. And again, like what we learned on this, you can tell right here, this part right here, doesn't that have negative sloping tangent lines? So it has negative values. Right here, this has positive sloping tangent lines, so it has positive derivatives, like that. So it matches everything with kind of what we thought about, say. Let's do the next one, and this is another one we can do with precision now. So if you want to make a table of values, you can do that. So we'll do x, and we're going to graph y equals x to the third. And I'm just going to use the same basic values. The same idea applies to this. So I'm just going to take the x values that I chose and do them to the third power, and you can do all this in your head. So that's 8. 1 to the third's 1. 0 to the third is 0. And then what's negative 1 to the third? That's negative 1. And then negative 2 to the third is negative 8. Okay, that's an odd function. Okay, it's got the characteristics of an odd function. So let's go ahead and let's graph that. Okay, so I've got 0, 0, and I've got 1, 1, then over 2, 8, and left 1, down 1, and then left 2, down 8 like that. So that's a cubic function, which you should be familiar with. So that's the graph of f of x equals x to the third. Okay, now if you look at your derivative on that, well, now that we know how to do a derivative, we can compute that. So if f of x is x to the third, what's the derivative now? 3 x to the second, right? By power rule, right? So that's a quadratic, okay? Now, if you do a quadratic, and just for accuracy, let's make a little table of values just for a couple of points on this. So we have x and we have y equals 3x squared. Now that's a parabola that's being stretched. That 3 is stretching it vertically. So let's just do the same values on this for a little accuracy and see what we end up getting here then. Okay. Okay, so I'm just going to do, we have 3 times 2 to the second. That's 3 times 4, so that's 12. I have 3 times 1 to the second. That's 3 times 1, so that's 3. Then the next one is 0, and so forth. Okay, and this one is an even function, so this would just match this, and then the 12 would match there. It's an even function, so it's got some symmetry about the y-axis, so that's how that would go. Now, if we plot those points, we'll have a precise, accurately drawn derivative on this now. So we would go left 2, up 12, up there somewhere, negative 1, 3, 0, 0, and so forth like that. So you have a parabola kind of like that then, okay? And what your goal on this is when you're doing that is to kind of see, well, does that derivative make sense to you, okay? Why I look at this is like this. That's very steep, right? That slope is very steep, so it's positive, very positive. But then what it's doing is getting less steep until it gets to 0. Then the steepness changes again like that. Okay, does that make sense? Okay. So you always have positive derivatives. The slope of the tangent line on the cubic's positive. That's why everything's above the x-axis. Okay, like we learned with derivatives. Okay, so that's just kind of an idea. You can actually, when you find a derivative, then you can make everything precise. Okay, now we learn a few more basic rules on this section. So what we want to do here is, this is what's called the constant multiple rule. And you'll use this all the time. So basically what you're using is, it says if you have a constant that's multiplied by a function, then you do this like this. When you do the derivative, you write down the constant, and then you do the derivative of the function. So let me give you a couple of illustrations of this that you can write down. Say that you had 2x to the fourth. Okay? What that is this function, you have x to the fourth, and then you have a constant. So what you really do when you do the derivative is you just write down the constant. You don't do the derivative of the constant, because the derivative of 2 is 0. Don't do that. Just write it down, and then do the derivative of x to the fourth, which is 4x to the third, right? So what you get is you get 8x to the third like that. So anytime that you have a function with a constant multiplied by that whole function, that's the way you approach it, is like that. Now you could certainly in this problem do this in your head, and that's what you're going to learn to do anyway, is you just do 4 times 2 is 8, then you subtract from the exponent, you got it like that, right? That's how you're going to do that anytime you have a constant. Does that make sense to everybody? So that's what we call the constant multiple property, okay? All right, now on what I want to do next with this is just show a real simple proof of this, because this is not a hard proof. So what we have is we have the function f of x equals k times f of x, not kx, kf of x is what we have. Okay, and we're going to put this in the difference quotient, so I'm just going to prove to you why that's right. So when I do this, when we do f prime of x, we got to go to the difference quotient. Okay, so to prove this, and you know, mathematicians who came up with all this stuff, when they're dealing with derivatives, you're generally always going back to that definition of the derivative. So we know that definition is f of x plus h minus f of x over h, and then you're doing the limit as h goes to 0. Okay, well let's set this up, and let's see kind of what comes out of this thing then. So that's going to be equal to the limit as h goes to 0, and then let's put everything in here and see what we get. Okay, all right, can you tell me what would go there? What did I give you? Yeah, okay, that's what we're working with, is that. That's what goes there, okay? So we're going to put a k f of x there. How about what goes here? What's the difference?
K f of x plus h.
There you go, good. K f of x plus h. You just change the x to x plus h. So what goes here is k times f of x plus h like that. Okay, now remember those limit laws that I had you do? Okay, well, they come in handy. If we didn't know the limit laws, we'd never be able to prove this. So what happens is, when you do this, you can factor that k out of there. So you have the limit as h goes to 0, and you can factor the k out of that to get f of x plus h minus f of x all over h, like that. Okay, so I just factor. That's just algebra. Now remember, in the limit law, we learned this basic thing. In a limit, we said that if you have a constant, what could you do with the constant? Pull it out of the limit. That's one of the limit laws we learned. So then you could write the next step as k times the limit as h goes to 0 of f of x plus h minus f of x over h, like that, and then we're done, okay? Because after all, what is this thing right here? What does that represent? That's the derivative. That's the definition of a derivative. So you can bring this down. The k comes down, and that thing I highlighted in yellow, all that is the derivative. So I just proved that the derivative of kf of x is just k times f of x, f prime of x. Does that make any sense? Okay. All right. All of these things come from, everything you're doing with a derivative when you're proving something has something usually to do with that difference quotient. Okay. All right. So the next thing we have is we're going to look at a sum and difference property. I'm going to do a proof of that because it's not too hard. And the idea with this is, I'll just give you a quick example. So like if you had something like x to the second plus x to the third. Okay, if you want to do the derivative of that, it turns out that all you do is you just do the derivative of each part separately. So that what's the derivative of x squared? 2x. What's the derivative of x to the third? 3x squared. So you do those derivatives and you just add them together. Okay, if that was subtraction, you would subtract them. So anytime you have a function that's separated with plus and minus signs, you just do each piece. Okay, does that make any sense? Okay, seems logical.
Do we have to put them in lowest or highest term first?
No, really with this one, you're done. Because, I mean, what you're doing is you're just doing the derivative of each part. And you're done. Okay, there really isn't any simplifying. I mean, you could factor an x out of that, but there's no, you don't have to. You're done once you do the derivative. Okay? All right, so here's how the proof would go. A lot of times students don't like proofs. I love proofs. If you're a math major, that's what you get into, is proving everything. It's awesome. Okay, so here's how we do the proof. Okay, first of all, I'm going to set this up like this. Okay, so I'm going to take the difference quotient. The key on this is you got to get this set up in the difference quotient. So this is what we're going to work on. I'm just going to do this. Okay, so what I do is I've got f of x plus h minus f of x all over h like this. Okay, well, you always approach these the same way. Whatever I gave you is going to go there, whatever it is. And I'm just going to put the plus or minus in there and do it at the same time, which is okay. So right there, I'm going to put f of x, and then I'm going to put like plus or minus g of x like that. Okay, so I have that. Okay, what do you suspect goes in this parenthesis? F of x plus h plus or minus g of x plus h, right? Okay, it's the only difference, okay? So we'll put in here f of x plus h plus or minus g of x plus h like that. Now we're going to rearrange this, and again, this has to do with limit laws. The limit laws are very important because they develop theories for us, okay, and properties and stuff. Okay, so what we'll have from here then is I'm just going to rearrange this, and I'll see if you guys follow this or not. So what I'm going to do is I'm going to be clever, and I'm going to put these things together. I'm just going to group them together. So when I do that, I'm going to write this as f of x plus h minus f of x, like that. And then I'm going to put that over h, like that. Then I'm going to be clever again, and I'm going to put these two together. Okay, and I'm going to go like this. So the next thing I'm going to do is write this as, this will end up being some sort of a plus right here when I do that. So I'm going to write this as g of x plus h, and then minus g of x. And don't worry about the plus or minus because it works its way out anyway. So it kind of goes like that. So that would be kind of the idea. I haven't changed the problem. What I did is I just split it apart into two fractions. You have a common denominator anyway. Okay, so if you think about this, just tell me if this makes sense to you. I mean, I split everything apart. So if you added those fractions, wouldn't you just get what I have here? Now don't worry about the plus or minus. I really should have put a plus or minus there. So that goes there, that goes there. It all works out. All the signs work out that way. All right, so I'm just splitting apart. Now what is that? That's the derivative of f of x. Okay, that's the derivative of g of x. And remember, we have a limit law that says if you have a limit of the sum, what do? The limit of both. Okay, so really what you do to conclude the proof on this is you just write this like this. Okay, so there's just one more key step. So we would write this as the limit as h goes to 0 of, and you don't have to put that bracket there really, f of x, whoops, not doing that right. So I need to write this like this. So we're going to do the limit of f of x plus h minus f of x over h, like that. And then plus or minus the limit as h goes to 0 of all this stuff over here, and then we're done. Okay, that would be f of x plus h, or g of x plus h minus g of x over h. And then we're done, because this thing right here, isn't that just the f prime of x? Okay, that's what f prime of x is, so that's what that becomes. And how about this thing over here? What's this? That's g prime of x. So see, it's the limit laws. The main thing I want you to see is just give you a little bit of a start on doing some proofs at this level and showing you that the limit laws, one of the reasons why they're important is because of these kind of things. Okay, without the limit laws, you wouldn't be able to make this determination. Okay, so there's a sequence to when you're building a mathematical theory. All right, does that kind of make sense what I did there? Okay. All right, now we're going to kind of get back to crunching out derivatives because we're going to look at these rules here, and we're going to kind of expand on our power rule and constant rule. So again, you want to learn to do this in your head. I'm going to write a step that's probably unnecessary on this. So what I'm going to do is, since you have a constant there, you just write the constant down. You don't differentiate that. You just write it down. And then what you do is you do the derivative of x to the fourth. So that's 4x to the third like that. Okay, well, what's the answer? Yeah. Now see, I don't mind if you do that in your head. You're going to do that in your head from here on out. It's just when you bring that 4 down, all you're doing is multiplying it by the constant anyway. So just do it in your head. But that's what the constant rule is saying. Okay. Then the next one, we want to do this. Okay. Now we worked on this a little bit today. Before you do a derivative of a square root, what must you do? You write that as a 1/2 power, right? You always have to write it as x to a power before you can do that derivative. So that's 1/2 x to the 1/2 like that. Now we're going to do the derivative. We're just adding in that extra feature now. So what I'm going to do is I'm going to write down the 1/2. I'm just going to write it down. That constant, just write it down. And then that comes down, and then do the derivative of this. And that's a power rule. So what you do is bring down the half. And then you would subtract 1 from the exponent. So I'm going to use 2 halves. Okay, so that way I have a common denominator. Does that make sense? Write the 1/2, do the derivative. Now put it together. So we're going to have a half times a half is a fourth. You multiply fractions straight across. Then you would have x to the negative 1/2 like that. Okay, so that would be one acceptable way to write the derivative, like we've been doing. You could also say 1 over 4x to the 1/2, right? And what else could you do? Back to a square root. Okay, so you want to be sure that you know that. So that's 1 over 4 times the square root of x like that. So that's how that would work out. All right? Does that look okay to everybody? Okay. Any questions? Okay. Okay. Now, continuing on with this. Now what we start looking at is we start looking at sums and differences. Now again, I'm going to write some rules, write this step out that's probably not necessary, but because eventually you're just going to do this all in your head anyway. So what I'm going to do on this one is d dx. Remember, that's the Lightness notation that's telling you to do a derivative. So we're going to do the derivative of 2x squared. Then we're going to do the derivative of x. Then we're going to do the minus. And then we'll do the derivative of 7. And I want you to write it that way, although when you're doing your homework and stuff, you'll just do this in your head, okay? Okay, now when you look at this part, see, I'm doing the rule that says you can break sums up into sums of derivatives. So when I do this, I just write down the constant. That constant comes out of the derivative. Now what's the derivative of x squared? 2x. Ah, how about this one? I wonder if you guys know this yet. What do you think the derivative of x is? I haven't even done that yet.
1.
It's 1. Why is it 1?
Because x to the power is 1.
Yeah, okay. All right, here's 2 ways to look at this. Okay, first I'll show you 2 ways to understand why the derivative of this is 1. If you did the power rule, look what you get. You bring down the 1, you subtract the exponent, you'd have 1x to the 0, right? Well, what's anything to the 0? 1. So you get 1 times 1 is 1. Now, I don't look at it that way. I look at it this way. Y equals x is a line, right? What is the slope of that line? 1. Okay, so like if you had y equals 3x, the derivative's 3. Okay? So if you have like a linear term, I call that a linear term, the number in front's the slope, so that gives that to you. Okay? Tell me what the derivative of 7 is. 0. It's a constant. Good. Okay, now we get the answer. So we'd have 2 times 2x is 4x. Plus 1, that would be the value of the derivative, okay? Now again, your goal on this process, just do it in your head, okay? But understand why you can do it in your head. Really all you do is just 2 times 2 is 4, x to the first. That's 1, that's 0. Like that, you just do it all in your head, okay? All right, any questions about that?
What happened to x to the first power?
Remember, I did the derivative of that. Okay, so we said over here, when you do the derivative of x to the first, you get 1. Okay, so it became 1 because I did the derivative. Okay, okay, let's take a look at this one. This one is d dz, so the variables I'm just using are z. So again, what I'm going to do is look at d dz, and I'm going to split this up into 2 parts since there's a sum. So I'm going to do 5. I'm going to write this as 5 halves z to the 4th plus, then I'm going to do the derivative of d dz of 3/4 z to the 2nd, like that. Okay. Now again, most of this you're just going to do in your head. So that's a constant. What do? You write it down. Okay. Now what's the derivative of z to the 4th? Or z to the 3rd. Okay, so we got that. Okay. Go to the next piece. 3/4 is a constant. Write it down. What's the derivative of z to the 2nd? 2z to the 1st, or just 2z, right? That's that power rule. Okay, any question? All right, now what do we do? Well, we just multiply it together, we simplify the fraction, so this is really 20 over 2. So you can just simplify that right now. 4 over 2 is 2, so what does that give you? 10z to the 3rd, right? Okay. The next one over here, you're going to have 6 over 4, because you multiply fractions straight across. If you do that, that reduces to a half. So what do you got? 3/2 z. Okay, so we would just write that as plus 3 over 2z. Then that would be the value of the derivative, like that. Okay? Is the fraction stuff okay? Tell me honestly. I always say calculus is about 80% of what I teach is algebra and review stuff, okay? The calculus stuff usually isn't the hard part for students, usually algebra. And you'll see that more and more. So are we good? Okay. All right. Now, this one right here, again, I'm going to write a step that you won't have to write, but when I do g prime of x, what I'm really doing is I'm just doing the derivative of each piece. So what's the derivative of 3x? I'll keep asking that because students a lot of times get puzzled on that. It's 3. Okay, isn't that just a line? And the slope of that line's 3, that's how you know, okay? What's the derivative of 4? 0. So what's the derivative? So you don't have to go through all that mess, okay? You guys know that. 3x minus 4 is a line, right? What is a derivative anyway? It's a slope of a tangent line. And isn't the slope of a tangent line to a line already a line?
Yeah.
So it's got a slope of 3. Boom, boom, you know the answer. I want you to know the answer immediately. Is that good with everybody? Okay. All right. Now, let's take a look at this a little bit. Now, you just have the same idea, but you have fractional exponents. So it's just fraction exercise. So I'm going to write this in Leibniz. You could say y prime, or you could say dy over dx. And then we're just going to do the derivative of each piece. Okay, and again, your goal on this is mostly just to do this in your head, but because I'm teaching you rules, that's why I'm writing this step out. Okay, so we are breaking up the sums into the sum of the individual derivatives, like that. Okay. And then we just got to focus on each individual part, and then we'll be done. Okay, so it looks like we have a power rule on the first one. So what I'm going to do on that's bring that down, and that's negative 2/3. And you can subtract in your head. You're subtracting 1, so I'm using 3/3, like that. Okay, then I'll just go to the next one, and then we'll kind of simplify as we go. Bring down the 3/2. Again, you write down the 2 because it's a constant. Just bring that down, and then that's going to be 3/2 x to the 3/2 minus 1. So I'm doing 2/2 like that. Okay? And then the next one, write down the 3. The derivative of x to the 3rd is 3 x to the second. Okay, and then what's the derivative of 4? 0. Okay, and again, just do anything you can do in your head, do in your head. That's the goal. So what we have is negative 2/3 x to the negative 5/3. Okay, notice on this one the 2's cross out, so yeah, you want to simplify stuff. So that will be minus 3 x to the 1/2. And then finally at the end you would have 3 times 3 or 9x to the second. Now you can go further than that. I'm just going to choose to stop at that point. What I usually tell students to do again is make your derivative match the form of the problem. The problem that I gave you had rational exponents. The exponents were fractions, so it's okay to have fraction answers. You can change it to radicals if you want to, but you're not required to. All right? Everybody follow everything I did on that? Okay? All right? When you do that, subtract 1, try to just get to a point where you can do that in your head regardless of the situation. Okay? Okay, so let's do, I'm going to let you do a little bit of work on these for a few minutes, down to number 8, because I'll make sure everybody's got the basics going on these. So let's go ahead and work a little bit on 1 through 8. If you can do them in your head, please give me the answer in your head, okay? I want that. That's the goal. A little bit. But your goal on these type of problems is to do them very fast and very efficiently, and you'll get there. Okay. Now, when you do this one, what's your answer on this one? You'd want to do this in your head. 48x to the third, right? Okay, because you can actually just take that 4 and multiply it by the 12. So that's 48x to the third. The exponent goes down 1. Okay, like that. Okay. The next one, you might want to write a step on this. Okay. What I'm going to do is, again, we write the constant down. And the derivative of x to the fourth, what's that? 4x to the third. Okay, then what? Reduce the fraction. Okay, you can either get 20 over 8 and reduce. You got to reduce somewhere. To me, it's always best to just reduce now. Okay, then I'm going to get, it looks like 5 over 2. And x to the third would be what that derivative is. Okay, like that. Okay? All right, solid? Okay, how about the next one? What's the answer? 9. Okay, it's the number in front of x. Okay, that's the rule, okay, for that derivative. If you forget that, what you're doing is you're doing, that's x to the first, you're doing 1 times 9 is 9, subtract 1 from the exponent to get 9x to the 0. Isn't that 9? Okay, don't look at it that way, just learn that the number in front of x is the derivative. Okay, the next one you want to have, write that as 1/2 x to the 1/2 to begin with. Okay, then the derivative f prime of x. Again, now you can multiply those now if you want to. 1/2 times 1/2 is 1/4. You can go ahead and do that in your head. Then you're going to subtract 1 from that exponent, so I'm going to use 2/2. Okay, all right, that looks like that's going to give 1 over 4 x to the negative 1/2. So that's a derivative. That's one way to write that. Okay, everybody solid with that? Okay. All right, the next way is you can go 1 over 4 x to the 1/2. So you can go that way. All right. Then on this one, I would prefer that you make it all the way to 1 over 4. Now change that back to square root of x. That's the answer I would be looking for. And that's because it started in radical form. I want it to end in radical form. Everybody good with that? Yes.
So, as a general rule, if you ever are taking the square root, cube root, fourth root of anything, it's always going to end up being that in the denominator.
Yeah, because it'll end up being well. It depends on. You could have an issue. You could have something like, if you had something like the 7th root of x to the 11th.
Right, but the 7th root will always be the 7th root. Because it's the denominator, so
right.
You're subtracting 1, so you're always
right.
keeping the
yeah, you will keep that denominator, so that's always going to be the same. If it turns out to be negative, then you move it to the denominator. It won't necessarily be that way because that power underneath the radical,
right, it depends on what
it depends on what that is, really. But you're right, the root would remain the same. Okay? All right, so the next thing on this one, we'll do this like this. Now, the way I'm going to write this is I'm going to think of this as just 1/9. That's a constant. That 1/9 is a constant. Then I'm going to think of this as x to the 2/3. So you'd want to rewrite it that way first of all. Then when you do your derivative, f prime of x, okay, you can just write down the constant. You can bring the 2/3 down. And then you can subtract 1 from the exponent. So I'm going to have 2/3 minus 1, so use 3/3 like that. Okay?
How did you get the 1/9?
How did I get what?
The 1/9.
Okay, because that is a constant. Think of that as being a 1 there. Okay, you got to look at your constant, and remember that's separate from your derivative. That's how I got that. Okay? All right, now what I have is 2 over 27. Okay, then I have x to the negative 1/3. So that is a derivative right there. That would be one answer. The next answer you could say is 2 over 27 x to the 1/3, like that. And then I would prefer you just take it back to the cube root because it started in that form. So the best final answer would be 2 over 27 times the cube root of x, like that. Okay? It's all arithmetic when you get right down to it, right? Okay? All right, the next one I'd want you to be able to do in your head. So I'm just going to write that above here. What's the derivative of 2x to the 8th? 16x to the 7th, okay. 8 times 2 is 16. Exponent goes down 1. What's the derivative of 8x to the 2nd? 16x to the 1st, right? 2 times 8 is 16. Exponent goes down 1. What's the derivative of x? 1. It's the number in front. So that's your derivative right there. Okay?
Does the sign change since it's -1?
Nope. Sign's the same. Because what you're doing is you're breaking up the derivative. Those signs are going to do the same. You're doing the derivative of the first, then plus the derivative of the second, minus the derivative of the third. The signs come down. Now you might encounter a situation where you might end up with a minus, so then you would transform that to positive. Okay, how's that look? Good, bad? Give me a sign. I have no clue. Okay, all right. This stuff is stuff that you got to get down as fast as you can this semester too, because the derivatives get more and more complicated as we go. Okay, the next one, g prime of x. Okay, I'm just going to do each piece separately. So I'm going to write down the 2/3. The derivative of x to the 9th is 9x to the 8th. Okay, that's your power rule. Then I bring down the minus. I write down the 1/4. And the derivative of x to the 8th is 8x to the 7th. All right, what did you put for the derivative of 2e to the 5th? Oh, outstanding. Okay, not 10e to the 4th. Everybody got that? E is a constant. It's not a variable, so that's 0. Okay, so we have that. Okay, now what I can do from here is that's 18 over 3. That's really 6. So that's going to give 12x to the 8th. And then 8 over 4 is really 2. So that's minus 2x to the 7th, like that. That should be the value of your derivative. Okay? A lot of arithmetic. Okay? Okay, next one. Let's see. Write this as 2t to the 1/2 minus t plus 2. Like that. And then when we do our derivative g prime of t, you can do this like this. Write the constant. Derivative of t to the 1/2 is 1/2. T to the 1/2 minus 1 is how you would do that. Okay, what's the derivative of t? I keep asking that because students a lot of times don't get that until after they practice this a while. And of course the derivative of 2 is what? 0. So that's the methodology you go through. Then we'll clean it up. Yes?
On number 7, isn't it supposed to be 6x 8? Yeah. So you're canceling out 3 and 9, so you get 2 times 3, which is
2/3, 9 over 3 is 3, isn't it?
Yeah.
Yeah, thank you. Okay, I didn't catch that. No, okay, so that's good. 9 over 3 is 3, so that would be 6. That's what you said, right? Is that better? Okay. All right, now let's finish this over here. So notice the 2's cross out. So that would be t to the negative 1/2 minus 1. Okay, and that would be one way to write the derivative. Second way would be 1 over t to the 1/2 minus 1. And then that could be written as 1 over square root of t minus 1 like that. And that's good enough. There's things you could do. You could get a common denominator and put that together, but you don't have to. Okay? Those are just want you to know how to deal with the radicals. Okay? All right, so is that going okay? Okay, now what we do is I've kind of given you all the fundamental derivative rules of this type. Now we start putting together problems that are, a little bit more work. At this stage, on these problems down here, you have to multiply these things out at this stage, okay? One thing that you cannot do is you can't just go through and just watch this. Don't write this down necessarily. If you did the derivative of 2x, you would get 2. If you did the derivative of what's inside, you'd have 3x squared minus 4 plus 0. You cannot do that, though. Okay, that rule does not work. A little later, and next week, we're going to learn about what's called the product rule for differentiation. You can't just do the derivative of two things and multiply them together. That does not work. So what you have to do, instead of doing that, is you have to multiply this thing out before you do the derivative. So I'm going to do a distributive property. So we're just going to do algebra first. So we have 2x times x to the third is 2x to the fourth. Then we do 2x times 4x is 8x to the second. Then we do 2x times 2 is 4x. That's how you have to start that problem, say. Okay? Now, we're just going to do the derivative now in our head on this one. Okay? So it's easy. Okay, do the power rule. So 4 times 2 is 8. Exponent goes down 1 to 3. Okay, then you got 2 times 8 is 16. Exponent goes down to 1, so it's just x the first. And then this is what I call a linear term, so that's just a plus 4, like that. So that's how that derivative gets put together. That would be the final answer to that derivative then.
Can you keep driving that?
Can you keep what?
Driving? Let's say keep doing that, so that would be 8 times by 3x.
Oh, you mean do a derivative again?
Again, yeah.
Yeah. I mean, we're not there yet, but you can do a derivative as many times as you want to. You can do a derivative of a derivative of a derivative infinitely, if it's differentiable. Okay, if the function's differentiable, that is.
So that means
Okay.
as long as you have degrees, you can keep this going?
Well, no, I mean you could eventually on this problem, if you did several more derivatives, eventually you'd get to 0. And it'd stay 0 forever. Okay, we'll get there. Okay, what do you suggest on the next one?
Well, foil it.
Foil, yeah, you got to foil first. You got to multiply, then do the derivative. So we got to do that. Okay, so to start with, do this. Okay, first term from FOIL, x times x, x squared. Outside term from FOIL, we have plus 6x. Okay, inside term, minus 5x. Last term, minus 30 like that. Okay, clean it up. So you're going to have x squared. The like terms go together to give plus 1x, or just x, minus 30 like that. Okay, so you got the algebra. You're going to FOIL and factor and stuff like that throughout calculus. Okay, now your goal on this is just quickly in seconds tell me the derivative. So what's the derivative of x squared? 2x to the first, right? What's the derivative of 1x? 1. What's the derivative of 30? 0. Now you don't have to write all that out. Again, the answer to the derivative is 2x plus 1. Now, to kind of go along with what we said, see, this is a quadratic. That's the graph of this function is a parabola. Notice the derivative is a line. So when you're differentiating, the power goes down 1, see. That's the idea. Okay? Does that look solid? Okay? All right, well, let's finish up with these next two here, and that'll be a good stopping point. So what you have to do is you got to multiply all this out. So this one you have to start by multiplying out, because we don't know the product rule yet. We're going to learn that next week. So the first term is going to be 2x to the third. When you multiply that, then you're going to do 2x times 4x, which is minus 8x to the second. Then we do 2x times 9, which is plus 18x. Okay, then you just start over again and go this way. So negative 3 times x squared is negative 3x squared. Negative 3 times negative 4 is positive 12x. And then negative 3 times 9 is negative 27. Does that look familiar? Okay, you start getting into heavy algebra background stuff at this point in the class from here on out. So now you got like terms, so put them together. So we'd have 2x to the third. Okay, these are like terms. The x squareds go together. Negative 8 minus 3 is negative 11x squared. Okay, put the x's together. 18 plus 12 is plus 30x. And then bring down the minus 27 like that. So see, you have to apply the algebra before you do the derivative. Now we're just doing the basic rules that we learned today. So do this. You want to just do this very quickly in your head. So first term, you're going to have 6x to the second. Second term, you're going to have 22x to the first. And then 30x, what's its derivative? 30. And then the derivative of 27 is 0. So you're done. That's it. Okay. That beats doing the quotient, the definition, right? F of x plus h minus f of x over h. That would be a pretty tough thing to do on that problem. Okay. Thank goodness we have all these rules. Okay, let's finish with this last one here. So we got g of x. Now, what I'm going to do on this, we're going to do a distributive property. So, and I'm going to write the steps just in case you don't see this. So we're going to just do square root of x times square root of x. Then we're really doing plus the square root of x times 2. Now we're dealing with radicals, so you know you got to work with fractional exponents. What's the square root of x times itself? X, right? Square root of x squared, right? And if you do the square root of x squared, what happens to the radical? Goes away. Algebra stuff, okay? So that's x. And then this is going to be, I'm going to write this as 2x to the 1/2 power. Okay, now I'm ready to do the calculus. Okay, so you need to multiply it out and prepare to do the derivative, see. Okay, now I'm solid. Okay, what's the derivative of x? 1. That's what I call linear term. X to the first is linear. Its slope is the number in front. Okay, then this one is a power rule, so we're going to write down the 2. It's a constant. And then do your power rule, so it's going to be 1/2 x to the 1/2 minus 1, like that. Okay, so that's going to give 1 plus, 2's cross out, that's x to the negative 1/2 like that. Okay, that is a valid answer to the derivative. And like we've been doing, I like you to write this as, also take it to that level, and then finish it up by taking it to the square root. So you'd have 1 plus 1 over the square root of x would be your derivative. Okay? So you're seeing on here you do a bunch of algebra, and it's next week it'll get more and more and more complicated. These are the fundamentals. That's why it's super important you get this down now. Okay? All right. So I'll see you next week.